Okay, the first thing we're going to look at with these motion problems are some motion problems in which the distance being traveled by two different people, two different objects, are going to be equal to each other. So the first thing I'd like to review is just the fact that when you have distance, when you have distance, the distance is equal to the rate that you're traveling times time. So something like if you were traveling at 60 miles per hour and you traveled for 3 hours, you would have then traveled a distance of 180 miles. Or if you're given, well, we could solve for any one of these. If you were given the fact that you traveled 240 miles at a rate of 60 miles per hour and you wanted to find the time, well, to find the time, it's 60 times the time is equal to 240. So to solve for time, you would just divide both sides by 60, and then the time that you traveled would have been 4 hours. So let's now take this one step further and kind of try and draw a diagram or a picture. So first I'm going to actually just leave that distance is equal to rate times time. And if we have two objects that travel the same distance, we're going to call one distance 1, and we say that it traveled the same distance as distance 2. We would say that distance 1 is equal to distance 2. Another way to kind of break that down, because distance is equal to rate times time, we can change this to the rate of the first one times the time of the first one is equal to rate of the second one, time of the second one. And all I did was I substituted this, instead of being d, I changed it to r times t. So I just substituted d for r times t. I substituted this d for r times r2 times t2. And two ways that this can look is if we have two objects, they start at the same place and they end at the same place. So that's distance 1 and that's distance 2. So you can have a word problem that kind of states that two trains left from the same place, they traveled the same distance, they give you the rate and the time of this one and maybe just the rate or the time of this one, and you have to solve for the other. So that's one example. Another example is if you have two objects, one travels in this direction and the other travels in this direction, but we know from the wording of the problem that their distances are still the same. We can still set up this equation right here, plug in the values that we know, and then solve for them. Alright, so let's take a look at an example of one of these. So I'm going to take this example. It says, on Tuesday, the express train made a trip in 12 hours. So, let's see. I'm going to say the rate of the express train, time of the express train was 12 hours. Okay, because it says the express train made the trip in 12 hours. On Wednesday, the freight train made the same trip. Now, because it's saying that the freight train made the same trip, we know that the distances of the two of them has to be the same because it made the same exact trip. So their distances are going to be equal to each other. So on Wednesday, the freight train made the same trip in 16 hours. So the time of the freight train, the freight train was 16 hours. Find the rate of each train if the rate of the freight train was 15 kilometers less than the rate of the express train. So now we kind of need to figure out, well, what are we going to do with these rates to plug some stuff in here? It says, I want to make sure I don't get off the camera here. The freight train was 15 kilometers less than the express train. So we've got the rate of the freight And the way I always start this is I make them equal to each other at first, and then I read the problem again and I figure out, do I have to add something to this side or add something to this side to make the statement true? It says the freight train was 15 kilometers less than the rate of the express train. So the express train is faster, so its number is going to be bigger. It said the rate of this one was 15 less. So what I would have to do is add 15 to this side to equal the rate of the express train. So the rate of this freight train was slower, so we need to add more to it to be equal to the same speed of the express train. And that's why the freight train was 15 kilometers per hour less than the rate of the express train. Okay? Our big equation that we know that we're going to have, okay, now I'm going to put this in here for RE. I know that it's equal to this now. It's equal to the rate of the freight plus 15. And now we can just leave this as RF. Okay? So now we have, we know that the distances were equal to each other, and the diagram that I would kind of use to show that would be that on Tuesday, this is the distance of the express train. He traveled a distance. On Wednesday, the freight train traveled the same distance. So their distances are equal, okay? So what we're going to do with that knowledge is we're going to say, okay, distance of the express is equal to the distance of the freight. I'm going to change this to rate times time instead. So I'm going to say the rate of the express times the time of the express is equal to the rate of the freight train times the time of the freight train. Now I'm just going to substitute what I have in here. For RE, I'm going to use this expression because that's what it's equal to. So I have RF plus 15 times the time, which is 12. That's equal to RF. We're just going to leave RF as RF because we don't have anything that we can substitute that. And we're going to put times 16. Now here, I'm going to have to distribute this 12 across these parentheses. So I need to multiply that. So 12 times RF is going to be 12 RF. 15 times 12 is 180, and that's equal to 16 RF. Well, now the only variable we have left now is RF, so that's what we want to solve for. I'm going to subtract 12 RF from both sides. I have 180 is equal to 4 RF. Well, to solve for RF now, I'm going to divide both sides by 4. So I'm going to come over here. Yep, I can. So 180 equals 4 RF. Divide by 4. Divide by 4. So the rate of the freight train, 4 goes into 18. 4 times, that would be 16, so there'd be 2 left over. Put a little 2 here. 4 goes into 20, 5 times. So the rate of the freight train, I now have found, is 45 miles per hour. And now we can find the rate of the express train, because that's just going to be RF, which was 45, plus 15. Oops. So that is equal to 60. And that's it for our first motion problem.